Conditional probability. The probability of an event may change if we know that another event has occurred. For example, suppose that a fair die is thrown and we know that an even number has appeared. What is the probability that the number obtained is less than 4? If we let A be the event that we know has occurred, i.e., that an even number has appeared, and B be the event that the number obtained is less than 4, then we want to find the probability of B given A. This can be written as the probability of B given A, which is equal to the probability less than 4 given even number appeared. This kind of probability is called conditional probability, i.e., the probability of B occurring conditional on the fact that A has occurred. To evaluate this, notice that as A has happened, it becomes the sample space. Thus, the sample space is equal to A, which is equal to 2, 4, or 6. So we have our Venn diagram down here, and we have a large rectangle, which in sets represents the universal set. In probability, it represents the sample space. We have the set A, which is now actually a rectangle instead of an oval. Set A was that an even number appeared, so set A contains 4, 2, and 6. They are all the even numbers. And set B contains all the numbers that are less than 4, so 1, 3, and 2. So set A has now become the sample space. That's why it's drawn in as a rectangle, because we know that this happened. We were told that one of the numbers was even. So the sample space is equal to set A, which is equal to 2, 4, or 6. And therefore n, which is the cardinal number of elements in the sample space, or the cardinal number of elements in set A, is 3. Also, the event B given A is restricted to that part of the sample space, which is less than 4, i.e., the intersection of A and B, which is 2. So remember, set A, which is now the sample space, are the elements that are even numbers. Set B are those that are less than 4. So 2 is the only element in the intersection. 2 is even, and it is also less than 4. Thus, OR is the cardinal number of elements of A intersection B, which is 1. There's only one element there. Then, the probability of B given A is going to be the number of elements in the intersection divided by the number of elements in set A, which is now the sample space, which is R over N, which is going to be 1 over 3. There's one element in the intersection, but there's 3 elements in the new sample space, which is set A. To relate this probability to the unconditional probabilities of A and B, notice that the number of outcomes in the original sample space is 6. 1, 2, 3, 4, 5, 6. There are 6 faces or sides on a die. If we divide above and below by this, we get the probability of B given A, which we know is 1 over 3. Got that from up here. We're going to divide the 1 by 6 and divide the 3 by 6. And 1 over 6 is actually the probability of A intersection B, because there's one element in the intersection, and the probability of A is 3 over 6, because there are 3 elements in set A. So the probability of B given A actually becomes the probability of A intersection B divided by the probability of A. This result is generally true and gives us the formula for conditional probability. So, definition of conditional probability: if A and B are 2 events, then the probability of B given A stands for the probability of B given that A has occurred. This is given by the probability of B given A is equal to the probability of A intersection B divided by the probability of A, which is the same thing as the probability of A and B divided by the probability of A. And in a sample space for which each outcome is equally likely, we also have the probability of B given A is going to be the cardinal number of elements of A intersection B divided by the cardinal number of elements of A. So A comes second in B given A, so A, or the probability of A, is our denominator. Whereas if the question had said the probability of A given B, it would be the probability of B would be the denominator. In practice, to tackle questions involving conditional probability, these are the steps. Step 1, identify what we know has happened, we will call it A. Calculate the probability of A, or the number of elements in A, if the sample space contains only equally likely outcomes. Step 2, identify what we now want to find the probability of, we will call it B. Step 3, identify the event A intersection B, i.e. that both A and B occur, and calculate the probability of A intersection B, or the number of elements in A intersection B, again, if the sample space contains only equally likely outcomes. Part 4, use the definition of the probability of B given A, which is the probability of A intersection B divided by the probability of A, or the probability of B given A, which is the number of elements in the intersection divided by the number of elements of A for equally likely outcomes, to calculate the conditional probability. So in short, it's really the intersection over what we're given.